Hi everyone, we are pleased to present our group project for assignment 2 in COM 3210/6210 focusing on spatial query processing using R-tree and Concur method. Our team member include Lakshmi who handled nearest neighbor search, Sravya who implemented Skyline search, and myself Azan Atar. I compiled the report, design visual diagram, and design this presentation. This assignment was about implementing and comparing spatial query processing algorithm. We focus on two fundamental problems: nearest neighbor search, which is task 1, and skyline search, which is task 2. We use 200 randomly selected query point on a synthetic parking dataset with 10,000 point in nearest neighbor search, and in skyline search we applied over the real world city dataset consisting of 2D points. To solve these, we manually implemented R-tree spatial indexes and used Python without any third-party libraries like R-tree or Skyfi. This added complexity but ensured full control over algorithm and behavior and data structure. Now I will come to our team responsibilities and tool. This project was divided among us to maximize clarity and efficiency. Lakshmi implemented and tested the NNN method from scratch and helped validate our tree performance. Xavier developed three Skyline search methods and conducted comparative runtime analysis. I oversaw the end-to-end documentation, authored our formal report, created diagram, and handled slide and script development. We all coordinated closely to ensure consistent code structures, output validations, and synchronized testing. The tool we used was Python 3, basic file input, Euclidean distance metrics, and custom R3 node.
The nearest neighbor sequential approach. We began task 1 with the baseline, the sequential scan. For each of 200 queries, we have calculated the Euclidean distance to every single point in the dataset. The brute force method is simple and reliable but quite expensive. It gave us an average time of 0.0539 seconds per query, making it a good reference to evaluate improvements from optimized methods. This step also helped evaluate the accuracy of our R-tree output. R-tree. Next, we implemented the best first search using a manually constructed R-tree. We used MinDist, a minimum distance metric from query point to bounding rectangles combined with MinHemp to explore only the most promising nodes. The traversal always selected the closest unvisited node first, allowing us to prune irrelevant subtree early. This drastically improved performance, reducing the average time of over 0.0208 seconds per query, a speed up of approximately 2.6 times over brute force. The third method applied a divide and conquer strategy. We split the 10,000 point data set by x-axis into two equal parts, built two separate R trees, and ran each query against both trees. This hybrid approach leverages both spatial partitioning and pruning. By dividing each space upfront, the algorithm could operate faster in two smaller trees rather than one large tree. The result was best performance, that is 0.0186 seconds per query, a total speedup of nearly 3 times when compared to sequential baseline.
In task 2, the goal was to compute skyline points. Those are not dominated by any others. Here, we tested three algorithms such as sequential scan, BBS, divide, and conquer. In sequential scan, we checked each point against every other, which took runtime around 0.671 seconds. And in branch and bound skyline, we used R3 and a min heap to print dominated entries, and the runtime was around 0.207 seconds. And in divide and conquer, algorithm, which splits the dataset, computes partial skylines, and merges altogether, and the runtime was around 0.624 seconds. All these three methods produced the same 9 skyline points, confirming the correctness of the results. Each approach highlights trade-off between simplicity and efficiency, with PBS proving to be the most optimized on our dataset. This diagram shows the logic of PBS algorithm. It starts from the root node, adds children to the min heap based on minimum distance, and iteratively expands the most promising entries. At each step, it removes dominated entries. This saves computational time. Compared to the sequential scan, BBS intelligently limits search to high potential candidates early on. This drastically reduces the number of comparisons, which is especially beneficial when dealing with the large datasets or small skyline sizes. In the divide and conquer method, the dataset is divided and each hop undergoes a skyline scan. The results are then merged recursively, preserving dominance logic. This technique benefits from reduced scan size per half, and then final merge ensures correct skyline filtering. However, merge operations are computationally non-trivial and depend on the number of output skyline points from each half. While not as fast as PBS, this method still offers meaningful improvements over sequential scanning, especially on larger or more uniformly distributed datasets.
Now let's talk about performance comparison table. This bar chart provides a consolidated view of the runtime across all six methods. For nearest neighbor, the sequential scan averages 0.0539 seconds per query above baseline. Best first search with R3 brought that down to 0.0208 seconds thanks to efficient running via Mendes. Divide and Conquer achieved the fastest time at 0.0186 seconds, which is nearly a 3x speed up over brute force. Now we will talk about for Skyline search. The sequential scan took 0.671 seconds while branch and bound processes reduced that to 0.207 seconds, demonstrating the advantage of combining help-based search with dominance filtering. Divide and Conquer landed in between at 0.624 seconds, still a decent improvement over the brute force and approach. Key takeaway here, the R tree clearly accelerates Spatial query not only in nearest neighbor search but also in skyline queries through branch and bound process. Divide and Conquer show consistently strong performance, especially when data sets are large or uniformly distributed. And importantly, despite the performance difference, all Skylines method returned the same set of 9 points, reinforcing output consistency and correctness. We all notice that branch and bound process perform best when Skyline sizes are small because fewer dominance checks are needed, while divide and conquer process shines on balance and well-partitioned dataset.
This slide shows some of the actual outputs generated during testing and validation. On the left side, we have nearest neighbor results, and on the right side, we have skyline outputs. The nearest neighbor results includes query points, nearest dataset points, exact distance, and the runtime per method. And the skyline outputs, which remained identical across all three methods, exactly 9 skyline points in each case. These results confirm the correctness of our implementation. All outputs were written to text files and compared for consistency. We verified runtime logs, number of comparisons, final outputs across all implementations. Also, we cross-checked sample queries to ensure that results from the R3 methods matched those from the sequential baseline. That was critical in validating the performance gain weren't coming at the cost of accuracy. We used these outputs not only for visual validation but also to debug edge cases such as overlapping points or near child distance. So these files were key in both testing and performance verification.
Now I will talk about challenges and key learning. This project offers a valuable technical learning curve. Challenges we face: manually implemented a balanced artery using STR packing, which required precise knot organization and recursive splitting. Handling skyline merge logic in the divide and conquer approach without losing accuracy. Creating a reliable runtime logging manually since we didn't use profiling tools. Now we'll talk about key learning. R-tree significantly boosts vital query speed by running unnecessary paths. Divide and conquer scale well for large dataset. Skyline performances improve with clustered MBRS. We had more time. If we had more time, we would explore bulk loading techniques or multi-level indexing to enhance tree construction and query speed further. Now, conclusion and contribution. To summarize everything we have covered, we successfully implemented and tested 6 distinct methods, 3 for nearest neighbor search and 3 for skyline search. Each one gave us a deeper appreciation of algorithm design trade-off, particularly between simplicity, speed, and scalability. Our custom R-tree implementation, while challenging, proved to be a cornerstone to improving query time. That divide and conquer logic to a more complex, consistently boosted performance without compromising correctness. Team contribution. From a teamwork perspective, each member brought critical value. Lakshmi focused on nearest neighbor method, ensuring correctness and speed optimization. Savya handled the skyline approaches, conducted rigorous timing tests, and result consistency check. I compiled all results, created diagram, and ensured our documentation and delivery reflect our technical depth. This project not only gave us technical skill, it taught us how to collaborate under clear division of tasks while maintaining shared accountability. Thank you once again for reviewing our work. This project challenged us at every level from tree balancing logic to runtime testing, and we genuinely enjoyed the opportunity to apply these concepts practically. We are now open to any question from you.